customer recently received a new turbine for their process. They want us to test for the power output of that turbine.
Okay.
And right here is a diagram of all the specifications of that turbine.
All right, well, let's get to work. So technically, I'm the assistant supervisor, but basically, I'm the boss.
Okay, so this is the diagram of the turbine they are using with the 2 entering streams and the 1 exiting stream. I use the overall energy balance to solve for the shaft work of the whole turbine. Since the system is in steady state, accumulation is 0. Also, potential and kinetic energy are negligible, so I'll just cross those out. And since there's no expansion or compression, work from those 2 phenomena are also negligible. Since this turbine is non-adiabatic, there's heat loss, and that heat loss is equal to 2% of the work produced by the turbine as shaft work. This leaves us with a reduced overall energy balance in which we will then solve for the enthalpy values.
So after doing some research, I found the enthalpies of stream 1, stream 2, and stream 3. Streams 1 and 2 can be found in appendix A1 under superheated steam. Stream 3 has a quality of 0.92. So this means that to solve for the total enthalpy of stream 3, we take the quality of 0.92 times the enthalpy of vapor plus the remaining 0.08 times the enthalpy of liquid. These added together gives us 1.5 times 10 to the 5th kilojoules per kilogram, and that's the total enthalpy for stream 3. We later plug these values back into the reduced energy balance and solve for the shaft work. After doing the calculations, we found that the work is equal to 61,735 kilojoules per second. We need to design a new compression system for our customer. The source of the air is 100 kilopascals and 300 Kelvin. It's flowing at a rate of 0.05 kilograms per second, and the goal of the system is that the final pressure must go up to 800 kilopascals. All right, you guys have until the end of the day to show me your designs.
Got it.
Show me what you got.
For my compression system, I decided to use an adiabatic compressor, followed by a heat exchanger, followed by a second adiabatic compressor. Over here, I have detailed the PV diagram of what this would look like. On the diagram, there are 3 distinct areas of work corresponding to the compressor, the heat exchanger, and then the second compressor. To solve for the first work of the compressor, I use these equations which rely on gamma, which is a ratio of heat capacities that for ideal diatomic gases is approximately 1.4. Using these equations, I rearranged to find the relationship for volumes, which I plugged in to solve for T2. I solved for T2 because I wanted to use this ideal work equation for adiabatic compressors. Once I had all my values, I solved for work 1, which is this area. After that, I solved for work 2, which is simply PdV, where V2 and V1 are retrieved from the ideal gas equations. After that, I solved for the work of area 3, which is again these equations using the new temperatures and pressures and volumes for that system. Once I had all of my works, I added them together and got a total work of 8,744 joules per second. Once I had my ideal gas calculations, I went ahead and compared my value for total work using an enthalpy diagram. Before I began, I had to convert my values because this diagram is in megapascals and degrees Celsius rather than Kelvin and kilopascals, which my original question was posed in. I calculated my delta H values using this diagram and the 4 points that correlate to the PV diagram data points. My delta H2, which corresponds to the area of work 2, was approximated to be 0 because I assumed that work in a heat exchanger is negligible. Once I had my 3 delta H values, I summed them up to get total work and got a final value of 10,250 joules per second.
For my system, I decided to use one single adiabatic compressor up here. So the inlet stream has a pressure of 100 kPa at 300 Kelvin, and the outlet stream is the desired pressure of 800 kPa. Here is a representation of the work on a PV diagram. So from this area, we can see that we have one single work to calculate. The T2 that I determined was 543.3 Kelvin, and with this, I plugged it into the equation for work and got a value of 8,731.9 joules per second. After calculating work from the ideal gas assumption, I wanted to compare my values to values from the enthalpy-entropy diagram. The enthalpies at these temperatures and pressures are 305 and 550. Calculated work to be 12,250 joules per second.
So for my system, I used two adiabatic compressors. From there, it flew into the second compressor to get the final result of 800 kPa, which is what the customer wanted. From here, you can see that there are two distinct areas of work. I used the assumptions of ideal gas to find the new temperature. I used the work CV delta T times moles to E1. We used a relationship of 5/2 R because we assumed it was a diatomic ideal gas. Our second temperature was 543 Kelvin. Second work to be 5,496 joules per second to give us a total work of 8,717.6 joules per second. Here I found my points 1, 2, and 3 from the PV diagram and found my H's. Here we then found the delta H's between point 1 and 2, and then again from point 2 to 3 to find an H total. From there, we also then multiplied by mass to get 12,250 joules per second.
See, I don't even think Kathleen's design is that good.
In each of the team's designs, I believe that Kathleen's two-compressor ideal gas design was the most efficient. Here are the calculations.
I agree with your conclusion. I'll call the customer tomorrow and let them know what design we're choosing. Great work.
We'll get him next time.
I don't even care what he thinks.